Hi, and welcome to this talk on 360-degree refactoring, tuning code to learn. Here's how. I'm Lynn Langit. Lately, I've been working with a group of people to learn to understand quantum computing applications, including Shor's algorithm, which for me has always been kind of like a mountain. I've got higher and higher, but just can't seem to get over the top. Specifically, I've been working on a weekly book club with this book, Programming Quantum Computers, and in a couple weeks I'm scheduled to lead the chapter on Shor's algorithm. And I'm feeling like I need to do more preparation. So I wanted to use a technique that I've used throughout my professional career to deepen my knowledge about technical concepts, and that's 360 refactoring. So I always do research before I get into this method, and I go to Wikipedia along with the other sort of go-to areas, and you can see that I'm justified probably in my approach here because part of this algorithm in Wikipedia, it literally says for the period finding subroutine of Shor's algorithm, the section may be too technical for most readers to understand. So what I'm really trying to do is I'm trying to find that place which will give me information, which will fill in what I got out of the book and get me further up the mountain towards understanding Shor's algorithm. The reason I'm making this presentation is because I use this technique in many different areas in my technical career, and it's really been useful to me, and I'm thinking it might be useful to you whether you're trying to learn Shor's algorithm or any other new to you sort of concept. So how does it work? Basically, there's 4 steps. The first step is for whatever you're trying to learn, if your current example is not complete enough for you, try running that example in a different programming language. So this book has a library for JavaScript called QC Engine that is made for studying and learning. And it's great in that it's accessible, but I'm finding that it's not enough for me to be able to confidently explain to somebody else how this algorithm works. So I want to try to find Shor's algorithm in a different programming language. Then when I find an example, I want to read everything about it. So not just the code, any documentation, any code comments, any explanation that I can find that's associated to it. The refactoring part, of course, comes in removing excess. So if in my exploration, if I find extraneous or duplicate information, I want to work to clarify that and to clean that for my own understanding, but then being a good technical citizen, I want to complete my refactoring and share it. I share most of my work in this area on GitHub. So I had a lot of candidate languages for this particular example. Just a quick search showed me all these languages listed here. And I honed in on a library from Google called Cirq. It's a Python-like library. And the reason is Python scripting language is simpler than for me to understand than C-based languages. Again, what you choose to use is going to depend on your language fluency around programming languages. For example, if you're a .NET person, you might pick Microsoft Q#. If you're a C programmer, you might pick Open QASM, which is an IBM language. So I found a candidate Jupyter notebook in the Google documentation called Shor IPython Notebook. So when I find an example, what I'm asking myself is how much time am I going to put into this and get a meaningful return? So how would I run this? Does it run without error? What result should I get? How long will it take to run and how much will it cost? Now my preferred way to run these kind of examples is on somebody else's cloud because I don't want to go through installing and trying to set up libraries and configuring on my local laptop. So I'm really happy if I can run in the cloud, and I'm really happy if I can run it as a service, which in the case of Google examples is often the case with the service they have called Colabs or Collaboratory. Now in looking at this notebook, it has an outline to it, and you'll see highlighted there on the order finding, it says there's 50 cells hidden. So one of the other evaluative areas that I look at in finding samples for refactoring is how complicated are they? And one of the things that I find in the Google world is sometimes it's overkill. So this is kind of a red flag for me. I'm not sure that this is going to be useful because I don't know how much time I want to put into refactoring 50 cells. I'd rather refactor 5 cells, for example. But I'm still going to use this as a candidate and see if it can be meaningful in my search here. So my next step, once I find the example, is to run it. And this is where, in this case, the Google implementation really shines. Just click a button and you can run it on Colab. Colab has a lot of compute available for free. It is constrained though, and if you want to run anything like production, you have to pay for the service or move on to the regular Google Cloud services. But I'm just trying out a little small example, so I want to make sure that their example runs quickly, and doesn't cost me anything. And that was trivial to do, which is great value. So one of the things that I have found, because I do use Colabs quite a lot and use Python as my second sort of test language, is most of the samples are runnable, but they're not always. So I always start by running it just to make sure that the sample currently works, because I don't really want to spend time trying to fix samples that don't work. The next thing is I want to verify that all the dependencies are installed, because I have run across quite a few notebooks, or not quite a few, some notebooks where there are missing dependencies in the notebook example, which if it's one, I can usually figure it out, but if it's more than that, it's a little bit difficult. And then the thing that I have found that trips me up quite a lot is a lot of times there's not version verification, and so notebooks will be created with an older version. So again, I don't want to spend a lot of time with this kind of stuff, so this is going to be a quick check, and if everything seems in order and the notebook runs, then I'll proceed, but if not, then I'm going to use a different code sample. So that worked, so that was awesome. And then I want to get into the core of what I'm going to be doing for my learning. And the first part of this is to read everything, which is a discipline, because a 50-cell notebook is non-trivial. So to read not only the code, but to read the comments, to read the text, because it's a notebook, and then if there are any plots or visualizations, to understand those. Now, the particular notebook that I worked with didn't have any like MATLAB type of plots. It did have ASCII art, if you will, so I can actually show you what it looked like here. Like that. It's visualizing a quantum circuit in this case. So that's a type of visualization, but I think every visualization, most visualizations, not every, will be really helpful when you're trying to learn something new. So the point is not just to read the code, read everything before I get to refactoring, which is 360 refactoring. So the next step before I start refactoring is to think about the path, and I take an information presentation principle that I've worked with for many years. The sort of summary of it is to group information in no more than 5. Units of 5. So 3 to 5 is kind of the range. A common thing that I see in examples, and this is an example of that, is information groupings are too large. They can go, 7 cells, 10 cells, 50 cells, and it's too much cognitive load for most people to learn a concept. So, introduce intermediate groupings, rewrite the groupings to have a path through the content. And that's in fact the next step that I did. So originally, Google was using a plugin for Jupyter, which is great to have a table of contents, but I was trying to kind of take an A, B, C, D, like what's step 1, what's step 2, what's step 3, and I was having difficulty with the existing outline because it just wasn't written like an outline I would expect. And so one of the first things that I did is I dug into it and refactored the outline. So you can see on the right side, what I did is I moved the copyright to the bottom, and I used the verb-noun format, which is more like writing in a book. So what are you doing? Testing Shor's algorithm, understanding order finding, using order finding, and then learn more. And then within understanding order finding, which you might remember is the biggest section with the 50 cells, I worked through what was being presented, and in my understanding there was a case A, which was classical computing for order finding, and a case B, which is quantum order finding. And that was helpful to me in being able to understand the concepts presented. So I updated the outline to show that. One of the things in general when I approach 360 refactoring is I approach it more with my educational background, which is linguistics. And in particular, I studied German. So this is weniger aber besser, which is less but better, which is a sort of beautiful and concise way to define what I think of as effective refactoring. So less but better. So very specifically, when I start to think about 360 refactoring, I look at duplication and errors. So duplication is not just within the code, because that honestly isn't too common, but between. So between the code to the comments and the type of comments. In this case, there's two different types of comments, which I find distracting, and the text to comments, which was duplicated, sometimes different, and the text to code. In terms of errors, I often find that because I'm working with large scale, quantum is known for scale and computational complexity, there will be examples that say, run this and wait 15 minutes, or run this and it could throw an error. And I'm not really interested in those examples. I want to see examples that run. So I actually remove that code. And then I remove comments that don't match the code. I might add comments or code to prevent errors. And I have an example of that because it was an error condition that was, I thought, kind of common but wasn't covered. Again, I want the code to be able to run. So now I'm ready to refactor. So I'm going to update, run, and repeat. And I have a 4-step process here. I want the code to be scannable. And in this case, I consider code anything on the page. So text, comments, or actual executable code. So I want it to be short, concise. I want to remove duplication. I want to be considerate of white space because that helps with legibility. And I want to think about diagrams or plots. As I mentioned, this particular example didn't have any diagrams. It didn't have any plots. It did have the ASCII art, but I think it could benefit from having more, and I did add more visualizations in my refactored version. So I refactored each of the cells, and there were 70 some, and my notebooks before and after, well, the before is the Google version, and my version are both available on my GitHub. But just to give you a sense of what I did, here's the before. And this is actually not bad, but I'll show you, in my opinion, what was more effective for me. So this is a simple function. It's a classical function. The function find factor uses the quantum order finder by default, in which case it is executing Shor's algorithm. So to be correct, it can be either quantum or classical. As mentioned, due to the large memory requirements for classically simulating the circuit, we cannot run Shor's algorithm for n is greater than or equal to 15. However, we can use the classical order finder as a substitute. Notice on line 1, we have a top-level comment, which basically duplicates what's in the text. Line 2, we have, to me, what is an extraneous comment, because all throughout this entire tutorial, n has been the number to factor, and this is like cell 50. In line 5, I believe it's an extraneous comment because the name of the method is called find factor, and it's explained in the text. And the output is in a separate cell, which is not useful to me, and it prints out an answer that I have to read the comment to understand, which is cognitive split, and I don't want to have that. So my updated version focuses really on the output. A pattern that I use is to print out meaningful output, and you can see I refactored it to say if p times q is equivalent to n, and if that's true, then the answer is correct. And then the result of this particular run is true. So it's, in my mind, easier to say if it's correct or not. I also added a topic using the classical order finder, and then very subtly, I reduced the amount of words in the text. And I also removed the extraneous comments, and I added a comment in line 1 as I was playing around and testing this. If you use a prime number, it actually fails, which I think, again, was assumed knowledge by the authors that I did not know until I tried, so I wanted to add it in. So in terms of code verification, depending on what kind of code, obviously if there's unit tests, that's great, but you want to have some sort of verification, which could be a print statement, In the case of some different computational environments like quantum, you sometimes put in what's called an observer or monitor, but you want to see each section, how you verify. That's important. Integration would be the whole notebook in this case, or sections of the notebook. And then there's also this aspect of running some code, outputting, and then plotting or visualizing it so that you can really more quickly get the results, which is a pattern that I find to be very effective in tutorials. So this is just meant to be, a little tip presentation. There's more to dig in. And the most probably interesting thing, I think, if you want to see my process in more depth, is to go to this third link down here, which is my GitHub repo associated to this book, and go to chapter 12, which is Shor's algorithm, and I have a folder for the Cirq experiments, and you can pull down both of the notebooks and take a look and do pull requests. I mean, if you have some suggestions to further improve, I would love to see them. But this method of 360 refactoring is one that I've used for years to learn more deeply different programming languages and libraries, and I wanted to take a minute and share with all of you today. Happy programming. I'm Lynn Langit.